Application problem. Rational functions. Question 13. The pressure exerted on the floor by the heel of someone's shoe is inversely proportional to the square of the width of the heel of their shoe. When Aarti wears 2 cm wide heels, she exerts a pressure of 400 kPa. Determine a function to represent the pressure P exerted by Aarti if she wears heel of width W. Part B. Sketch a graph of this function. Part C. If she wears spike heels with a width of 0.5 cm, what pressure does she exert? D. What do the slopes of tangents of the function in part A allows you to conclude about the rate of change in the pressure as Aarti decreases the width of her heels? Okay, so read the question again, try to understand, and then do it yourself. You can stop the video meanwhile. Here are my suggestions. Then look into my suggestions and try to understand a way to solve this problem. Okay. First part of the problem is to determine a function to represent pressure P exerted by Aarti as she wears heels of width W. Now, let's read the problem once again. The pressure exerted on the floor by the heels of someone's shoe is inversely proportional to square of width. So, keywords here are inversely proportional to square of the width. Right? So, pressure, and when Aarti wears 2 cm wide heels, she exerts a pressure of 400 kPa. So, that gives you the constant of pressure. Okay. So what we can conclude from here is that the pressure P is proportional but inversely to width W, correct? So we can write P is proportional to 1 over W square, that is square of width. So now you understand this. Someone's shoe is the pressure exerted on the floor by the heels of someone's shoe is inversely proportional to the square of width. That is what it means. Do you understand? If something is inversely proportional like this, then there will be a proportionality constant. Let's call that as K, and then it becomes equal to. So equal to W square. That is how we are going to develop this equation, right? Now, when Aarti wears 2 cm wide heels, she exerts a pressure of 400 kPa. That means P is 400 kPa if width is W. So that helps us to find the value of K. So let me put 400 for P. We have 400 equals to K over 2 square. Correct? So that gives us a value of K as 1600. Correct? So from here we can solve this equation. Correct? Let me push it a bit forward. I need more room to work. And so we get K equals to 1600 from this equation, right? And therefore I can write P is equal to 1600 over W square. Okay, so you understand how we got the equation, correct? So cross multiply. This is 2 square is 4. 4 times 4 is 16, correct? Cross multiply. And you get 1600 as the value of K. Now, we got the equation, that is part A. Sketch the graph. So it is like inversely proportional graph, right? So let me kind of sketch it here for you. Okay. Now, remember one thing. Width is positive, correct? So it is always on this part. It cannot be 0. If it is 0, for example, if it is 0, it has to be a vertical asymptote, right? And second, it is always positive. So think this as a vertical asymptote. I know width cannot be 0, that's why we have this kind of vertical asymptote. Now, if W is, as it is increasing, we found that the function is decreasing, correct? Yes. And when width is like, it cannot be 400 centimeter cube, well, as the width decreases, the pressure increases, right? If W is 1, let's say W is 1, then we have pressure of 1600, correct? So let's say W is 1, that means 1 centimeter wide, right? So we have something like 1600. If W is 2, that means divided by 4 is given 400. So it like exponentially decays very fast. Do you see how fast it decays kind of? So if width is more, the pressure is very low. But if width is small, then the pressure is going to be very high. So the graph will look like this. Okay? And you can put some points on the graph which are useful for its accuracy. For example, if W is 1, this is width in centimeter, and this is kPa pressure. Pressure in kPa. Okay. That's the pressure. So if W is 1, then the pressure is 1600. Let's say that is our point. If width is 2, then pressure is 400. So 2, 400. Let's say these are our points. Okay. Now that's the graph. If she wears spike heels with width of 0.5, what pressure does she exert? So 0.5 is like half. Okay. So let's do part C. So part C is pressure as a function of, so I could have written this equation like this. Pressure as a function of width is 1600 over W square. So that helps me to write this equation as pressure when the width is half. Let me write 0.5 as half. I love fractions. I'm not scared of it. I kind of like them, right? So this is the first part. It helps. I'll show you how. So 1600 over W square, which is half square, right? It is as good as writing 1600 times 4. So that much pressure. 4 times 1600, right? Because half square is this. So that is the kind of pressure which is going to be exerted, right? So which is equals to 2 zeros, and 4 times 6 is 24 to 64 kPa. It's important to write down the units here, right? So that means if my width is half, that means I'm here, then the pressure here will be 0.5 and 6400. See, it just exponentially, very fast increases, correct? So that is what the pressure is. Part D. What do the slopes of tangents of the function in part A allow you to conclude about, let me write, to conclude about the rate of change in the pressure as RT decreases the width, right? So you can see for here, it's kind of slope is like this, right? And here slope is very steep. Do you see how steep it is? As the width increases, the slope decreases. Do you see that? So as the width decreases for the heel, the pressure increases very, very high. So rate of change, we'll say, is extremely high as the width decreases. So we say rate of change is extremely high as width decreases, correct? So that is how we can do this question. Thank you.